Hello everyone and welcome back to the channel. So far we've done our LangGen series. If you haven't watched that, I'll put a playlist link down below and then you can check it out. And in that LangGen series, we've learned how to build LLM powered applications step by step. We have explored chains, agents, retrievers, and even tool execution. We saw how LangGen helps us connect large language models with external data sources, APIs, and other tools. But as we started building more complex systems, you might have noticed something missing. LangGen is actually great for creating individual component, but when you try to build multi-step workflows or systems where an LLM needs to make choices dynamically, things start getting a bit messy. You have to manage the control flow manually, handle intermediate steps, and sometimes even patch the logic together with if-else conditions. It works, but it's not scalable and it's definitely not elegant. So that's exactly where LangGraph comes in. LangGraph takes everything we've learned from LangGen and gives it a structure. It lets us represent our LLM workflows as a graph with nodes for actions and edges for choices paths. In simple terms, it's like giving our agent a map to follow so it knows what to do, when to do it, and how to handle intermediate results. With LangGraph, we can build stateful, reliable, and controllable AI systems where every step is transparent and the workflow is easy to debug, modify, or extend. So, if LangGen was all about learning the tools, LangGraph is about learning how to orchestrate them intelligently. And that's exactly what we're going to do next. We're starting a brand new series on LangGraph, where we'll go from the basics all the way up to building advanced multi-step agentic workflows. So get ready, because if you loved what LangGen could do, LangGraph is going to take things to a whole new level. So let's get started. In the last video, we talked about why we're moving from LangGen to LangGraph, and today we're taking our very first step into it. So imagine you have a chatbot that takes some input, let's say a name, and then it needs to process that information step by step before giving a response. So in LangGen, we'd probably just call a function or a chain directly. But in LangGraph, we think differently. We treat our program as a graph, a flow of states moving through connected nodes. Each node represents a specific action or step, and the state carries data as it moves through those steps. In the example that we'll be doing, our state is just a collection that holds a single key, which is messages. Think of it as a small memory that keeps track of whatever our chatbot knows at the moment. Then we will define a node, a simple function that takes this state, modifies it by adding a friendly greeting, and then returns the updated state. That's all a node does. It only transforms data. Next, the graph connects the dots. So we say when the process starts, go to this node, execute it, and then end the process. It's like drawing a mini flowchart. Start, then do something, and then end. So when we run it, LangGraph automatically handles the execution. It passes the state through the node, updates it, and gives us the final result. The output you see isn't just a printed message. It's the outcome of data flowing through structured logical graph. And that's the beauty of LangGraph. You're not just writing code anymore. You're designing a process. A process that's visual, controllable, and scalable. So in the upcoming videos, we'll slowly build on this foundation, adding more nodes and more edges and eventually intelligent choice making to our graph. So stick around, because this simple example is just the beginning of how LangGraph turns logic into flow. So let's go to the example now. So I'll be creating a new folder here, and then I'll call it LangGraph. And then inside this, I'll create my first file. So basic graph.ipynb. We'll do this in the notebook format here. Okay, so first of all, I need to install LangGraph here. So LangGraph, let me run this. And then once LangGraph is installed, we're ready to build our first graph here. So from typing, import typed dict, and dict. We'll run this and then select the interpreter here, Python environments, and then our recommended interpreter is this one. So as you can see, it can run the interpreter. Okay, I'd also like to import from LangGraph.graph, import state graph, start, and then end. Okay, this is going to be our first import here. Okay, our first cell is running. Now I'd like to create a class called my message state, which will have a type ticked as inside it. So inside this, I'll have a simple message that will be in the string format. Then after this, what I'm going to do is I'm now going to define my graph directly here. So my graph will be from state graph, and then inside this I'm going to pass my class that I've just created. So I'll add nodes to this graph. The first node will be we need to provide a string name to this, let's say initial, and then provide a function here, so greeting node. Okay, so this particular function needs to be implemented on top of this. Let's write down this function, greeting node. This is always going to have this parameter of this class that I've just created, and then it is going to return the same class that we have. Now, okay, what does this do? This is a simple node that adds a greeting message to the state. Okay, so let me write state, or basically update the state here. So up until now, this is all empty. Now I'm updating this. So I'm writing hello hello plus state message, whatever we have in message, plus and then maybe give full stop and welcome to LangGraph. Okay, so this is going to be my function, and then I've already added it as a node in my graph here. So we only have one node for now. Now we're going to add edges to this node. So graph.add edge. It is going to, at first we'll start the first flow is going to be, or the first edge is going to be from start to this particular node here, which is initial. And then after this, I'm going to add another edge from initial to end. So we'll only have one single node for this particular code here. So I'm going to compile this. So to compile, we only need to do pot equal to graph.compile and then run this. Okay, so we have some error. I think it's some spelling mistake here. So this should have been initial. Let me run this again. Initial, right? Okay, this is wrong here. So initial. Okay, our graph is compiled. If you want to print this, you can also directly run bot, and then you can see that we have one single node. We begin with the start part, then the process flows through the initial node, and then it goes to the end. So this is our basic graph workflow in LangGraph that we've created. So now, in order to invoke this graph, what we need to do is we simply need to invoke this bot object that we have, and then we need to pass something here. We'll pass messages and then pass our channel name, Learning Hub here. And then we'll print our response. So what happens here is, at first, the initial state in this particular variable contains this string called Learning Hub. Then it moves to greeting node, and then along with that Learning Hub, the state is now updated to this complete message here, and then basically what we get in the end is that particular complete content that we have processed. So if we run this, okay, something is wrong here. So message or messages, let's see. Message, state message. Let me just see if I've done any kind of spelling mistakes here. Okay, so this must be message. Okay, so if you see the response, then you can see, okay, why is it only showing just one response here? I have invoked bot, right? Something that I've not done here is return state, because it should return the updated state here. Let me run this again. And then if I run this, so it adds some new text as per the process function or the greeting node function here. And then it gives me the response. So this is a very simple implementation of our graph flow or our workflow using our graph here or using LangGraph. So I hope you understood the concept of LangGraph and then how it varies from LangChain. In the last two videos, we explored the basics of LangGraph, how nodes represent logical units of work, and how the flow between them creates an AI reasoning pipeline. But until now, our examples worked with simple single message states. In this video, we're taking the next big step, moving towards structured states that carry multiple pieces of information together, just like an agent's memory. So think of state as a data package. It holds everything your graph needs to process, pass, and transform information at each step. We'll start with the code and then I'll try to explain the code accordingly. So let me create a new file here. Complex graph.ipynb. First of all, from typing, import type dict and list. Let me run this and then select the kernel. So it's running from LangGraph dot graph import state graph comma start comma end. Okay, so these are the imports that we'll be needing. So the cell is running. Now I'm going to create a class that contains our state here. So class agent state, and then the type will be type dict. Inside this, I'll have a name, I'll have age, I'll also have skills, and then a result. So, unlike our previous video, instead of just one text, our now states contains multiple attributes like a person's name, age, and skills. After this, we'll be creating our nodes here. So for the first node, we're going to create a function. The parameter will be our agent state. And I'll write a doc string for this. This is the first node. And then here, I'm going to update my state here. So the result variable in the state will be updated. State name, welcome to the system. Then I will return the complete state here. Okay, so this is going to be my first node. Similarly, I'm going to type in the second node now, def second underscore node. Again, it will have a parameter of state. The node will always have the parameter of state, and then it will return the entire state here. Write a doc string. This is the second node. And after this, I'm going to update the state result again here. But first of all, I'm going to bring out my skills and then convert them from a list to a string. Dot join state skills. And finally, I'm going to update my result. So state result plus you have skills in state skills. And then again, I'm going to, or let me just do skills here, not state skills, because I've already extracted my state skills from this. So again, I'm going to pass out the entire state here. Okay. So each node in this particular graph that you see here, or the graph that I'm going to build, reads these structured states and then does its task and then passes it forward, enriching it step by step. So the first node here acts like an initial greeter. It welcomes the person into the system, and then the second node that I have adds more context, like the skills that they have, and then I'll also have a third node here. So what's that? Let me write down. Third node will contain an state, agent state again, and then it will return agent state for now. So let me write down, this is the third node. And then here what I'm going to do is I'm going to update my state equals to state result plus, let me add something more here. So in string, you are state age years old, and then end the string here. And then again, I'm going to return the state. So the third node completes the flow by including the age, creating a full personalized summary here. So the data flows from one node to another, gradually building the final message, just like a well-organized thought process inside an AI agent. So now we'll build that particular graph. So let me run this. It's running. We'll define a state graph, and then inside it, I'll have agent state. Then I'm going to add my first node. First node will be first underscore node, comma. I will now define the function with that first node. Then I'll also have a second node similarly, and then the third node. Let me copy this down. This is going to be my second node. And then finally, I'll have my third node. So I'm going to add ages now. So first of all, we will go from start to our first node. Then we'll go from first node to second node. Then we'll go from graph.add underscore age, second node to third node, and then finally after third node, we'll go to end. Let me compile this. So let me write an object name bot equals to graph dot compile, and then print out the bot here or the graph here. So as we can see, it goes from start to first node to second node to third node and then finally to the end. So the three simple nodes here highlights the true power of LangGraph. It helps you modularize reasoning, breaking large tasks into small, reusable logical units that form a clear and more traceable path of execution. So instead of handling everything in one complex step, LangGraph lets you think and build in stages, exactly like how agents reason in real life. So we'll complete this and then see the result here. So let me build my input state. I'll type out the name here. Name can be Alice. Age and skills can be this one here. So I don't need to pass in the result yet because that will be formed from within the nodes, and then I'm only going to pass until this skills here. So let me say data science. Okay, then finally what I can do is I can invoke the bot using this input state and then finally print out my response. So my response will be printed. First of all, what will happen is it will go to this particular node here. So it will take our name and then it will say welcome to the system. With this entire message, it will add you have following skills, and then after that, along with this entire message, it will add the age of the person and then we'll print the response. So let's see. Skills. Okay, what is it? Skills. What else here? Okay, here I've done some mistake, added an extra space. So let me run this again. And then as you can see, the result is Alice, welcome to the system. You have skills in Python, ML and data science, and you are 30 years old. So based on the flow of data in between these nodes, the result has been updated, or basically some extra strings have been appended in each of these results here. So I hope you understood the code and then understood the concept of this multiple node that we have been implementing here. So far we built a linear graph that processes structured input and composes a final result step by step, right? But this is just a beginning in LangGraph. In the upcoming video, we'll take this concept further by introducing branching logic, where your graph can make choices dynamically based on the state. In the last video, we learned how data can move from one node to another, with each node performing its task and enriching the overall result. But what if your workflow needs to take different paths depending on certain conditions? That's where things start to get interesting. Because in real-world AI systems, not every query or task follows a single linear route. Sometimes your graph needs to choose where to go next, and LangGraph allows that using conditional edges. So in today's video, we're going to see how to introduce choice making inside your graph, how it can intelligently choose between multiple nodes based on logic you define. First of all, we'll write the code and then I'll explain you the code here. So let me create a new file. Conditional graph.ipynb. I'll have some imports. First of all, from typing, I'm going to import typedict. Then from LangGraph.graph, I'll import state graph, start and end. Let me run this and then select the default interpreter. After that, we're going to write our agent state. So agent state is going to be of type dict, and I'll have number 1, which will be an integer, number 2, which will also be an integer, operation, which will be a float, string, and then I'll have a result which will also be an integer. Okay, so this will be our agent state here. Let me run this too. Now I'm going to create few nodes here. First of all, the first node will be adder. It will contain state, agent state, and it will also result or return an agent state here. Now here what I'm going to do is I'm going to write a docstring. So this node adds 2 numbers. After this, I'm going to update my final number, or I can sorry, it's not final number, it is result. So state result equals to state number 1 plus state number 2, and then I'm going to return a state here. Okay, then I'm going to define another node here which is called subtract, and state, agent state. The node will basically subtract 2 numbers, and then what I'm doing here is doing number 1 minus number 2 and then returning the state. Now I will define a router node here which chooses where should I go next. So decide next node. It will also contain an agent state. It will be of type agent state, and then it is simply going to return a string here. So this node will decide or will select the next node of the graph. Now I'm going to check one state called operation here. So if state operation double equals to add, then what I'm going to do is I'm going to return add operation, and then else if state operation is subtract, then I will return subtract op. Okay, so this will be my router node here. So let me run this. Then after this, I'm going to create my final graph. My final graph will be based on state graph, and then it will contain this agent state object. So agent state class. Let me add nodes here. So the first node will be add underscore node, and then the function for this node is adder. Second node is subtract node, and then the function for that is subtract. Then I'm also going to add a third node here. So graph.add underscore node. The third node will be named router, and then what I'm going to do here is I'm going to pass the state as it is here. So it will also be called a pass through function. So whatever we get will just be passed through that router stage here. So now I'm going to go and add edges. So first edge is going to be start, and then it will go to router. Then I'm going to add conditional edge here. So add conditional edge. What will this be based on? So this will be based on the router node, and then what will happen here is its function is this one, decide next node. So the function is here, and then the two options from this node is one is the add op, which will take us to add underscore node, and then the other is the subtract op, which will take us to subtract node. So basically we're referring to add op and subtract op from this particular node here, and then if we get add op, we'll go to add node, which means our adder function, and then if we get subtract op, we'll go to our subtract node, which is our subtract function. Okay, and then what we also need to do is, since both of these add and subtract will show the result and then go to the end of the graph. So what we need to do is we need to add two different edges here from add to end and then subtract to end. Now since this is done, I'm going to compile my graph. Let me compile my graph, and then if I print out my graph here, we'll see that first of all we'll start from here, then we go to the router node. The router node fixes where we should go next based on the agent state called operation here. If we get plus, then we go to add node. If we get minus, we go to subtract node. From either of these add or subtract node, we go to the end here. So this is how we can introduce conditional graphs in our LangChain. Now I'm going to declare my input state here. So input state is going to be the number one will be 10. Let's say the number one is going to be 10. Okay, I'll keep it 10. Number 2 is going to be 4. I don't need this result here. A result will be operated on its own, and then basically operation is minus. Now if I invoke my boat using input state, and then if I print my final response, then I can see that the result is set, and then since the operation is subtract, so the result is 6. If I change this operation from plus, now the result goes to 14. So either of these two nodes are chosen based on the operation state present in our agent state here. Okay, to summarize now, we start with an agent state that carries our data, two numbers, the operation we want to do, and either addition or subtraction. Next, we define two nodes, one that adds, one that subtracts. But the real magic is inside this router function here that we have. So this function acts like our choice maker. It inspects the current state and then returns which node the graph should go next. So if the operation is positive, then we go to add node. If the operation is negative, then we go to the subtract node. So LangGraph then uses these conditional edges to make it run. So these edges dynamically connect the flow at runtime based on the conditions, based on the condition functions output. So instead of a single linear chain, what we have here is it is a conditional chain, and it behaves like an intelligent tree, so capable of branching out and adapting to the data it receives. So this concept, conditional routing, is at the heart of making agentic system flexible. So in the upcoming videos, we'll take this concept further, including memory as well as message passing inside LangGraph, so your agents can remember and react contextually, and that is where LangGraph truly starts to feel alive. In the previous video, we learned how to create conditional routes in LangGraph, where our graph intelligently decides which node to visit next based on user input or data state. But what if we want to chain multiple conditional flows together, like a series of choices where one operation leads to another? That's exactly what we're going to explore today. So in this video, we're taking things one step further and see how LangGraph can handle multiple branching routes, letting you create more complex and intelligent workflows that don't just stop after one choice. So we'll first write down the code, and then I'll explain you the code here. Okay, so let me create a new file here. _complex conditional.ipynb. So first of all, I'll have my code. I'll have my imports here. So the import are going to be from LangGraph.graph import state graph start and end, and from typing I will have type dict. Let me choose the interpreter, and then while this runs, I'll create my agent state. So agent state, this will be have a parameter of type dict. So type dict, I'll have number 1 here, number 1 as integer, number 2 also as an integer, and I'll have number 3 as an integer, number 4 also as an integer. I will have operation 1 as a string, operation 2 also as a string, and then I'll save the result of operation between number 1 and number 2 in result 1, which is going to be an integer, and similarly operation 2 for number 3 and number 4 is going to be saved in result 2, which is also an integer. Okay, so let me run this. So while this is running, now we'll create our functions here. So first of all, we'll have adder, where we'll pass the parameter as agent state. It will again return an agent state. So I'll update state result 1 equals to state number 1 plus state number 2, and then I will return the state here. So let me copy this and then create another subtraction operation here. So I will have subtractor 2 or sub. Okay, I'll write the full function name subtractor 2, where I'm going to subtract these two, number 1 and number 2 here. Similarly, I'll have adder 2 and subtractor 2. So let me just copy this down and then copy it here. So here I'll have adder 2, the result will be stored in result 2, the numbers are number 3 and number 4. Similarly, in subtractor 2 we are going to store the result in result 2, where the numbers are number 3 and number 4. Okay, we also need to create two router functions, so let's do that. Choose next node 1. It will have a state of type agent state, and then it will return a string. So if state operation 1 is equal to plus, then what we want to do is we want to return add 1. Else if state operation 2 is equal to minus, then we want to return sub 1. Okay, I'll also create a router for our number 3 and number 4 part here. So choose next node 2. Okay, sorry, this has to be operation 1, and then here we'll have operation 2 add 2 operation 2 sub 2. Okay, so these are our router nodes. Now we'll go on to create our graph here. So graph equals to state graph. I'm not sure why the suggestion is not being shown, but anyway, agent state, I can just type this. First of all, I'm going to add my first node here. So the first node is adder 1, and then I'll give a name adder 1 here. Similarly, I have my second node, add underscore node. This is subtractor 1. Let me write down the function name here, which is, okay, what did I name it? Okay, subtractor 1. Subtractor 1. Similarly, I have added 2 and subtracted 2, which I'll just create here by copying this. Added 2 and then subtracted 2. Now I'm going to add a node for router 1 and router 2, which will basically act as a pass-through function here. So router 1 will pass lambda state and then basically pass the state here. And then similarly in router 2, this should have been a comma. Okay. And then in router 2 will do the same thing. So router 2 lambda state. Okay. Now what we'll do is we'll start adding edge. So the first edge is going to be from start to router 1. Then I'll add a conditional edge here. So add conditional edges. Now the detail of this conditional edges is from router 1, it will go to the choose next node 1, and from here we have two options. We can either go to okay, what is the function name? Let's see. So add 1 and sub 1, right? So we can either go to add 1. So if add 1 occurs, then we go to adder 1, and if sub 1 occurs, we go to subtractor 1. Now I'll add one more edge here. So add edge from adder 1 to router 2, and then subtractor 1 to router 2, whichever works in the following case here. Adder 1 and subtractor 1 both should go to router 2 here. Now I'm going to add another conditional edge for router 2 here. So the name is router 2, comma, and after this the function is choose next node 2, and then within this I'll have one more I'll have add 2 which will go to adder 2, and sub 2 which will go to subtract 2. Now after this I'm going to add two edges, either from adder 2 to end and subtractor 2 to end again. Now this is my final graph. Let me compile this, graph.compile, and then if I print the bot, then we will see our conditional graph here. So from start we'll go to router 1, and then either to add 1 or sub 1 depending upon the operation, and then we'll go to router 2 and then add 2 to sub 2 depending upon the operation that we have. So now what we're going to do is we are going to finally run this using our input state. Let me provide the input state. I'm just going to copy this here. So number 1 is 1, number 2 is 2, the operation is plus. So basically we need to see the result 3 in result 1, and then in case of number 4 and number 7 we need to see the subtraction operation here. So now what I'm going to do is result equal to bot.invoke, and then provide the input state here, and finally we print out the result, and then we can see our result here. So what did we do here? We started by defining an agent state that holds two separate mathematical operations. So each operation has its own pair of numbers and operators, one for each step and then one for the second. Now we define 4 simple nodes here, 2 adders and 2 subtractors. So each of these nodes does the operation and store the result back into the state. But the interesting part here is the 2 routers that we have. So router 1 and router 2. So these routers act like our checkpoints where choices are made. The first router looks at operation 1 and then chooses whether to go to the first adder or the first subtractor, and then similarly for the second router again. So LangGraph handles this beautifully with multiple conditional edges joined together, allowing our graph to branch and rebranch as per needed, just like how complex reasoning systems work in the real world. It's a simple yet powerful demonstration of how LangGraph gives you total control over your workflow's direction without any hard-coded if-else change in your logic. So now, instead of having a single choice, your system can make multiple sequential choices, each one based on the updated state of the graph. So this opens the door to designing more intelligent multi-step workflows like multi-turn reasoning, agents, multi-stage data processor, or even complex system that can react to evolving inputs. So far in this LangGraph series, we built conditional and multi-step workflows, graphs that decide where to go based on the data in the state. In this video, we're going to make things a bit more fun and interactive. We'll design a mini number guessing game using LangGraph, where the system makes guesses, checks its progress, and keeps looping intelligently until it gets the right answer or runs out of attempts. This example shows how LangGraph can handle iterations and choice loops, something that's incredibly important when you want your agent to keep reasoning, refining, and trying again, just like humans do when solving a problem. Okay, so without any delay, let's first go into the code. So here I'm going to create a new file. We'll call it number game. Number guess game .ipynb. So from LangGraph, I'm going to import state graph, start and end. From typing, I'll import type dict and list, and we'll also import random here. So let me select the virtual environment. I'm going to create a class called agent state. Agent state. So here I'll have three variables here. The first one will be name, which is going to be a string. The second is going to be a number, which is going to be list of integer. This is basically going to contain the guesses that the model makes, and a counter, which will also be an integer. So at first we'll have a greeting node, which will contain agent state as its parameter, and it will again return an agent state. Let me write down a drop string here. So let me say greeting node, which says hi to a person. So here what I'm going to do is I'm going to update state name to hi there. I have a state name that I'll pass in the input here. So state name. We will start the game. And what I'm going to do is I'm going to set state counter to 0 and then return state. I'll have another state called or another function called random state. This will contain agent state, so this is going to generate number, it will be random between 0 and 10. So state number will be appended with the random number guessed by this model here, 0 to 10. And then I'm going to update the state counter. State counter will be updated by 1, and then I'm going to return state here. The third function will be a router function, which will say should continue, contain an agent state that will return a string. So this will be a function to decide what to do next. What to do next. Here, if state counter is less than 5, I'm going to enter loop where this will be my state counter value. And I will return loop here, and in the else part I'm going to exit the loop and I'll return exit here. Now let me create a graph using the state graph, and inside this I'm going to pass my agent state. I'll add a node, graph dot add node. So first of all, we'll have a greet node using greeting node function. Then I'll have a random node using random state function. I'll also start adding the edges. So first of all, the first edge will go from start to greet. The second will go from greet to random. And then here we're going to have conditional edges. So add conditional edges. It will start from a random. The function that it should check is should continue. And we'll have two different cases here. The first case, if it's loop, then it should go to random, or if it is exit, then it should go to end. Now I'm going to have one more edge here. If the counter is greater than 5, then I need to end this loop. So one edge will be from random to end. So let me initialize my graph or compile my graph. And if I print my graph, okay, what's wrong? Let's see. So add edge. Okay, add edge edge. Okay, as you can see, so once the model greets the user, then it will enter inside this random node. Then a loop will be carried out if it stays within a certain condition, or else it will exit. Now, what I'm going to do is I'm going to take my input state here. So input state equals to name Shake, and the number list will now be empty. And with this, I'm going to invoke my bot with my input data, and I'm going to print my response. So if we run this in loop 1, loop 2, loop 3, loop 4, loop 5, because we've entered a condition for the value less than 5. So in loop 1, it gets 10, in loop 2, it gets 8, 7, 2, and 3, and respectively. So this is how we initialize loop in case of LangGraph. So we'll go to our very beginning of the code, and then we'll see what is happening here. So we start by defining this agent state that holds everything about this game. So it holds the player name, the target number, the last guesses, the total attempts, and the range of the number it can choose from. Then we have three things. We have the setup node. So this basically initializes the state, resetting attempts as well as the guesses. Then we have the guess node here, and then we have the decision node or the router node that we have here. So this is where the power of the LangGraph shines. So instead of using a while loop, we simply create a conditional edge that loops back to the same node until a certain condition is met. So the condition is placed here in this particular part of the code. So each loop iteration updates the state, meaning LangGraph remembers the previous attempts, making the upcoming choices context aware. So essentially, we've not completely implemented the game here, but we've turned this simple guessing game into an autonomous iterative reasoning process, which holds the same mechanism behind how our agentic systems plans, act, and retries while solving complex tasks. And I'm going to end this video for now, but what I want you to do is I also want you to add a target number here, and then basically in this particular router function here, basically check if the model has correctly guessed the number or not. If the model has correctly guessed the number, then the model has won the game. Or if the model has correctly or if the model could not guess the number within the given number of attempts, basically the model has lost the game. So I think you can implement that by yourself. In the last video, we explored the basic structure of LangGraph, where we learned how nodes and edges form the foundation of state-driven AI workflow. We built a simple example that took an input message, processed it through a node, and returned a response. Now, we'll take that idea one step further. In this video, we'll connect our LangGraph with a real AI model, Google's Gemini 2.5 Flash, and see how a complete interaction loop can be created between a user and an intelligent agent. Here, we'll represent our state as a collection of messages, each message capturing the conversation between a human and the AI. The power of LangGraph truly begins to shine here. Instead of hardcoding a linear sequence of actions, like we often did in LangChain, LangGraph lets us visualize and manage the flow of thought, where each step is an independent node that can evolve, connect, or branch dynamically. And by the end of this video, you'll understand how a LangGraph-based chatbot can process user inputs, generate intelligent responses, and maintain conversation flow, all through a graphic structure. This marks our first step towards building intelligent agent, multi-step conversational AI systems using LangGraph. So let's get started and see how easy is it to make your AI think in graphs. So we'll proceed to the code. I'm going to create a new file here. I'll name it AI agent, agents.ipynb. First of all, start with the import. From typing, I'll import typedict and list. Then from LangGraph.graph, I'll import state graph. start and end. Then from langchain underscore core dot messages, I'm going to import human message. Then the model, import chat Google generative AI. Then from .env, I'm going to import load.env. Load the credentials first, and then I'm also going to load the model here. So the model is, as I said earlier, it is Gemini 2.5/model. Okay, so let me run this. I'll select the interpreter and then create an agent state here. So the agent state will be of type dict. I'll have one single messages, which will be a list of human message. Then I'll have a function called process. I'll pass in the state, agent state, and then this will again return agent state here. The response will be invoked from the model here. So whatever is present in the state will be passed to the model, and then I'll get the response here. What I'm also going to do is I'm going to append the same state messages dot append response, and I'll also print this. So AI has passed this response dot content. Let me also add a line break here, and finally let me return state here. Now after this I'll pass state graph, and inside this I'll pass agent state. Let me add a new new node first. So the node name will be process and the function name is process. Let me add two different edges here. So add edge, start to process. Another edge will be from process to end. Process to end. Now compile the graph, and then we can see the workflow of our graph here. Okay, run this agent state, and then we can see our graph here, which goes from start to process and then to end. So basically in the process part, what happens is whatever message is being typed by the user is sent to the model or the AI model, and from there the AI model generates a response. Okay, now what we'll have here is a user input. Let me ask for the user message from the user input. Enter your message, and I'll run a loop until the user types exit. So not equals to exit. And I'm going to print the human message. And then my input state is going to be the messages. Its key will be messages. it will be a list of, or I can do it like this. I can code it under human message. Invoke the bot using our input state, and then basically ask for another user input again. So if I run this, I can pass any message here, hello, and then the model has replied me back. Ask what is your name, and then AI replies me back as well. So my each time I enter some text, that will be taken to the model. It will be invoked within our model, and then our model will generate some response here. So this is how we integrate a real world AI into our LangGraph workflow. In our previous video, we saw how to build a simple conversational agent using LangGraph, one that could interact with a real AI model and respond dynamically to human input. But what happens when we want our AI to do more than just talk? What if it could reason, maybe perform calculations, or use specialized tools to find answers? That is exactly what we will do, or what we'll explore in this video. We're introducing the concept of tool nodes in LangGraph, a powerful way to let your AI agent call external functions like the functions you've created and many more. Instead of relying on the model to guess or hallucinate results, we give it direct access to real tools, and LangGraph handles the flow between model calls and tool execution seamlessly. Here, we also use conditional edges, the graph that chooses whether the model should stop or continue based on whether there are tool calls remaining. This introduces intelligent flow control, something that was often more complex to manage in LangChain. By combining the reasoning power of language model with the precision of actual code functions, we're moving closer to a truly capable AI system, ones that can both understand and act. And by the end of this video, you'll see how the model calls the right tools, performs the operation, and keeps reasoning step by step, just like an autonomous agent. And this is where LangGraph begins to bridge the gap between intelligent thinking and practical execution. So, without any delay, let's dive in and see how your AI can now think, plan, and calculate all on its own. So now, let's jump to the code. I'm going to create a new file here. 6 underscore tool calls dot ipynb. First of all, we'll write the imports. From LangChain core messages, we'll have dot messages import. I'll have a base message, and I'll have a system message. Now about the model, this will be my model, and then from LangChain core dot tools, I'll import tool. Then from LangGraph dot graph dot messages, I'll import add messages. Then finally from LangGraph dot prebuilt import tool node. So this should be message, not messages. Now everything is important. Let's run this. And this is running. First of all, we'll define our model here, or first of all, we'll load the credential, then define our model as Gemini 2.5 Flash, and then run this. In the next node, I'm going to define my agent state. My agent state will be of type ticked. And then inside this, I'll have messages, which will be an annotated sequence of base message, and then in between I'll write add messages function. Okay, now I'm going to create a few tools. In this particular case, we're going to write 4 different functions or 4 different tools for addition, subtraction, multiplication, as well as division. So now we'll create the functions for them. So add the tool, def add a integer, b integer. This will also return an integer here. Let me write down the doc string. This will add 2 numbers, then return a plus b. Similarly, we'll do the same for subtraction, but I'm just going to copy this code multiple times: subtraction, multiplication, as well as division. Let me change the function name. This will be sub the 2 numbers, so subtract the 2 numbers. Here we'll have a minus b. This will multiply the 2 numbers. Multiply. Here we'll have a into b, and then this will divide the 2 numbers. Divide, and then a divide by b. Okay, so these will be my tools for this particular system. Now I'm going to list all my tools under this my tools list. So add sub, mult, and div. Now after this, what I'm going to do is I'm going to bind my tools with the LLM. So okay, we have our model. So model dot bind underscore tools. Let's say my tools. Okay. Now we'll create our nodes here. So I write the function for those nodes. So model call will be our first node here, which will have a type agent state, and it will also return agent state. So the system prompt is going to be a system message, and its content will be, you are an AI assistant. Please answer my query to the best of your ability. Okay. Now I will provide the inputs. So inputs will be our system prompt plus the state messages that we have. Then I'll invoke the model with this inputs. Inputs, and then finally I'm going to return messages. So this is going to be state messages plus response. Okay, I will have another router node here, which would say should underscore continue. It will contain agent state as its parameter, and we'll have message equals to state messages. I will pick up the last message from here. So message -1, and then if the last message does not contain any tool calls, then I will take the flow to end or the conversation end, or else I will continue with the conversation, so as to allow the model to call those tools here. Okay, so these are my nodes. Let me run this. Create a graph from state graph. Agent state graph dot add underscore node model underscore call will be represented by model call function. Then here I'll have a tool node object from class tool node, and then it will hold all of my tools from my tools list, and I'm going to add a node called tools using tool node function. Okay, so now I'm going to add edges. So graph dot add edge. The first will be from start to model call. The second will be a conditional edge. It will go from model call to the function should continue. And if the result from should continue is end, then it will end. Or else if it is continue, then it will call tools. So I'll have one more edge here, graph dot add edge tools to model call. And I should have one more, I guess, graph dot add edge model call to end. Let me compile this and then see the graph. So if you visualize the graph, you can see that we start from here, we go to model call. If it is a tool call, then we go to continue and then call the tool, and again we go to the model call. Or else if there are no more tool calls involved, then we go to the end. I'm going to create a function here called print underscore stream. This will contain a stream object. So for S in stream, I will pull up the last message. So if is instance message tuple, then I will print the message, or else message.pretty underscore print. Okay, now this is going to show the stream of operation that will happen while our tool is being called. So now we'll define our input. So input will be messages, and then it will be from our user, and the message will be add 40 and 12, and then calculate the product with 6. Also tell me a joke at the end. Okay, we'll not do 40 and 12, we'll do maybe 2 and 4, and then and then the product with 6. And then at last, I'm also asking the model for a joke. So what should happen here is this particular part should be done using our tools. And then for this particular part, the model should call the LLM, and then the LLM should be able to generate the joke without using any tools, because there are no tools present to generate the joke. Now, at last, what I'm going to do here is print stream. So bot.stream stream. Now inside this, I'm going to pass input and then stream node. Sorry, there should be a comma here. So stream node equals to values. Okay, now this brings us to the end of our program. If we run this, we should see a stream of operations that has been happening in order to fulfill our current operation. But I guess we have an error. Let's see what the error is. Okay, I've removed this last part. So let me run it again. Okay, I think I might have found the error here. So what I'm going to do here is node underscore name, comma node underscore value equals to next iteration s dot items. And inside this, I'm going to check if messages is present in node underscore values, and if it is present, then what I'm going to do is so message equals to message minus 1, and then node value equal to node underscore messages minus 1. Sorry, I missed this. Node value. So message minus 1. Let me run this again. What happened here? Okay, extra bracket. So as you can see, our query is taken, and then these first two numbers are taken as 2 and 4 here, and then passed to the add tool. The result is 6. Then both of these 6, and then the following 6 is taken as A and B, and then the multiplication tool is called, and then the product is calculated, and at last the joke is also generated. So this is how we can implement our own tools in case of LLM in LangGraph. In the last video, we explored how LangGraph lets your AI not just think, but act. We saw how to connect tools like addition, subtraction, multiplication, division so that the model could reason, calculate, and decide its own next steps. Now, we're taking that idea even further. In this video, we're building something more practical, a document editing agent powered by LangGraph. We'll call it an email drafter, your intelligent writing assistant that can update, modify, and then save document automatically using AI and tools. But before we jump into the code, we'll try to understand what's happening conceptually. Here, our agent can combine LLM reasoning using Gemini, tool nodes for doing real-world actions, and conditional graph control to keep interacting until the document is saved. We'll define two tools here, update and save. Update to modify the document content dynamically, and save to store the final version into a TXT file. The system prompt that we're going to provide will ensure the AI always knows what the current document state is, and the LangGraph manages when to loop or exit depending on whether the user has saved the document or not. This structure will make your AI truly stateful, capable of handling multiple user interactions over time, and goal-oriented, something that's much harder to achieve in plain LangChain. By the end of this video, you'll see how LangGraph turns your language model into a functional writing agent, one that just doesn't respond, but works with you to create and save real content. So we'll dive in and bring email drafter to life. So I'm going to create a new file here. Call it email drafter.ipynb. Write down the imports. Okay, we'll load the credential first, and then we'll also define our LLM here. Run this. And then we'll have a global variable to store document content. So we'll write document content equals to an empty string. Now we'll have our agent state class. Any other messages will be of type annotated, sequence, base message, and then add messages. Now, as I said, I'm going to define two different tools here. So the first tool will be update. We'll have a string content inside this, and then we'll also return a string content here. So I'll write down the doc string. Sorry for this. So this is going to update the document with the provided content. Update. Okay, so I'll access the global document content here. Then what I'm going to do is document content equal to the content that I get here, and then I'm going to return a string here which says document has been updated successfully. The current content is document content. Okay, so this is my first function or my first tool function that I have. Next, I'm going to create another tool called save, where I'll provide a file name in string format, and then I will return a string here. Write down the doc string, save the current document to a text file, and finish the process. The arguments that I'll be passing here is the file name, so which will indicate the name of the text file. So again, I'm going to access the global document content. Then if there is no file name created, then I will provide a file name.txt file here. Then I'll try to open this file. As file And I'll try to write the document content into this file, and then print document saved successfully as file name, and then also return the same. If we have an exception, then I'm going to return an error message here. Okay, so these are my two tools that I'll be using. Finally, I'll create a list of my available tools. So the first one is update, and then the second one is save. I am going to bind my tools, bind the LLM using my tools. So my tools, and then I'm going to create a tool node object using my tools here. Okay, now I need to define my nodes. So our first node is going to be our agent. It will contain agent state type. It will also return an agent state. So what I'm going to do here is I'm going to provide a system prompt. Let me just copy this prompt from somewhere. System. Okay, I'll just copy this entire thing from somewhere so that you can pause the video and then see what the actual prompt is. Okay, so the prompt is you are an email drafter, a helpful writing assistant. You're going to help the user update and modify document. If the user want to update or modify content, use the update tool, and then if the user want to save and finish, use the save tool. Okay, so this is done. The current document content is also passed here. After this, what I'm going to do is I'm going to check if user message is not provided, and based on this I am ready to help you update a document. What would you like to create? Okay, this is the first message that the user will be seeing, and then I am going to encode this inside human message, or else if there is already some content that has been generated, then the user input is going to be, so this should be an input. What would you like to do with this document? Then I will print user, and then print the user input. Then put it inside the user message again. Okay, now these two states are done. What I'm going to do is I'm going to combine the system prompt as well as the user message that we have. So this will go inside all messages. It will have system prompt plus list of state messages plus user message. Now I'm going to invoke the model response equal to model.invoke, invoke using all messages. Sorry, it's model here. Okay, then I'm going to print out AI response here. or just write down AI and then print out response.content. Now I'm going to check if there is any tool calls provided in this particular response. So if has ttr response tool calls and response dot, sorry for the autocomplete part, response dot tool underscore calls, then I will print which tool is being used right now. So invoking tool, please be careful with the brackets here. So tc tool name or tc in response dot tool calls, and then I'm going to return the messages which will be the list of state messages plus user message as well as the response. Again, I think I missed a bracket here. Okay, this one extra bracket extra. Okay, so this is done. So this is for our agent node here. Now I'm going to create a router node. So router node will be shared continue, it will contain agent state, and then it will return a string. So the doc string for this, determine if we should continue or end the conversation. Okay, so first of all, access our state messages. And then if there is nothing, then we should continue, or else if there is something inside this, then we reverse the list and then check the instance and see if it is save or like if the tool call name is present is in the form of save. So is instance message, it is message, right? Okay, so message and then tool message. The spelling is wrong here, so for each instance message and then tool message and saved in message dot content dot lower. Still this is not complete, and document in message dot content dot lower, then we return end, or else we return continue. Okay, so our router node is also fixed. So what we're basically saying is if we don't have anything, then we should continue. If we have save, then we should end the flow, or else if we don't have save, or like if we have update, then again we should continue the flow. Okay, so this is done. Save this call our state graph, add a node, this will point to our agent, add another node, I'll have tools. Now I'll start adding edges. So from start we go to agent, and then from agent we go to tools. And after this I'm going to add conditional edges here. We'll start from tools. We'll go to should continue function. And then from should continue function, we have two options. If we have continue, we go to agent. If we have end, then we end our flow. So let me compile this graph.compile, and then print out our state graph here. So as you can see, we start from here, we go to agent, we go to tools. If we have to keep on updating our document, then we continue this particular loop here from agent to tools, and then tools to agent. And then once we call the save tool, then we go to the end of the conversation. Okay, now I'm going to create some function for prints. So print underscore messages, it will contain our messages. Inside this function made to print the messages in more readable format. Okay, so if not messages, we just return. If nothing is there, we just return empty. But if we have messages, and then we especially focus on the last three messages that we have, then what I'm going to do is I'm going to check if is instance message is a tool message. Then I'm going to print out tool message result.content. Now to run the document agent, I'll create a new function. So at first the state is going to be messages and then empty message. Then let me run this. So first step in bot.stream state, if messages in step, then print messages, step messages, and then it's done. And then at last we can print out conversation ended. Okay, so let me run this. And then finally call run document agent. Now if we run this, so what it asks me is, I'm ready to help you update a document. What would you like to create? So write me a leave requesting email for 22nd October, sorry for the spelling, October 2025. Write me an email. Okay, the AI says, what should the email say? It should be about leave application. So the AI agent does write me an email. Now I want to replace the start date, replace start date to 22nd October and end date to 23rd October 2025. Let me save this file directly. Or I can say the email should include my name as Abhi, and then it does replace my name here as Abhi. So everything is done. What I need to do is I need to save this file. So if I say save the file now, save it. So it asks me for a file name, so I can say email draft, and then if we see somewhere in our folder location, then we see that we have an email draft file where the AI generated content is saved here. So this is all about the email drafter application. I've made a few changes here in this particular part here, as well as in this particular cell here. So please go through the changes, and then I hope it runs on your end as well. So in this video, we've seen how we can use LangGraph as well as our real world AI model to invoke the tools that we have and then do something meaningful for us. In this video, we'll see how we can build our RAG agent using LangGraph. So let's start our video by creating a new file, 8_rag agent.ipynb. Well, for this RAG agent, I'm going to use a file. I have a PDF file that I'll be using. So let me paste that file here first. So this is a stock.pdf file. I'll be using the data from this particular file for this RAG agent here. Okay, so now first of all, start with imports. Import type dict, annotated, and sequence. Now from LangChain core, I'm going to import something called human messages, tool messages, system message, and base message. So import human message. I don't need AI message. I'll need a tool message and a base message and a system message. From operator, import add as add_messages. Then I'll open the model or import the model, import chat Google generative AI as well as the Google generative AI embeddings. Then from LangChain community, I'll import PyPDF loader to open the PDF file. PyPDF loader. Then we'll import recursive character text splitter, LangChain.textSplitter, import recursive character text splitter. Then for the vector database, I'm going to use Chroma, import Chroma. And finally, for the tool part from LangChain_core, I'm going to import tool. load the credential first. Then I'll load my model here. The model will not be Gemini Pro. I'll remove the temperature for now, but it is going to be Gemini 2.5 Flash model. And for the embedding model, I'll be using so model equals to model slash Gemini embedding 001. Okay, let me run this. First cell, and the cell is running. Okay, there is some error here. Let me see what the error is. So Gemini 2.5 Flash should be correct. Okay, it should not be model name, but it should be model. Let me run it again. Okay, the model is imported. I'm going to copy this, not put it here, but put the PDF file inside this LangGraph folder so that it can be easily accessed by the notebook file present in this folder. So PDF path equals to stock.pdf. So this is going to be my PDF path. And then we'll try to load the file first. So for that, what I'm going to do is I'm going to check if the file exists or not. Path.exist PDF path, but like if it does exist, then I'm going to do PDF loader equals to PyPDF loader PDF path. Okay, this is also running. Now I'm going to load the pages from the PDF path. So load the pages from the PDF. So I'll put it inside our try block PDF loader.load. Let's also print something. So a PDF has been loaded and has a certain number of pages. If it cannot be loaded, then we'll load an exception and then print out our exception here. An error occurred while loading PDF, and then simply raise an exception. So our PDF has been loaded and then it contains 9 pages. Now what we're going to do is we are going to use our splitter here. So text splitter equals to recursive character text splitter. The chunk size is going to be 1000 and then the chunk overlap is going to be 200. That's okay. I'll keep that for now, but you can change the values according to your need. If you want to make smaller chunks, more smaller chunks, then you please reduce the chunk size. And then if you want to overlap some information between chunks, then you increase the value of the chunk overlap. So now let me split the pages. So pages underscore split equals to text splitter dot split document pages. So if we want to see total number of chunks, then we can print it out, and then we can see that we have now divided it into 24 chunks. If we reduce this chunk size to maybe 500, then we should see that the chunk that our chunks are, or the total chunks number should be increased here. So if we keep it to 500, then we go to 60 chunks, but right now I'll keep it to 1000 and then we have 24 chunks. Okay, now we go to our vector database part. So for vector database, I'm going to give a collection name. So collection name is going to be stock market. So we'll try to create a vector store from this one. So vector store equals to Roma.from documents. So document equal to page split. For embeddings, I'm going to use my embedding model, and then for collection name, I'm going to use my collection name. And then finally, we're going to see our success message here. But if we run into any kind of exception, then we'll print an exception and then raise some error. So if we run this, it will take some time to be vectorized, but our vector store has been successfully created, means that try block has been executed successfully. Okay, now we'll define our retriever part. So for retriever, we'll do vector store dot as retriever, and we'll define our search type. Search type will be based on similarity, and then the search keyword arguments will be we'll keep it for 3 for now. So the retriever part is also executed. Now we define our tool. This tool will be our retriever tool, which will contain a query of the form string, and then it will again return a string here. Provide a doc string for this. So this tool searches and returns information from the stock market performance report document. Okay, we're going to invoke our retriever using our query. So retriever dot invoke query. So if nothing is found with similarity to query in our document, then we print out or we return no relevant information found. Or if something is found, then we are going to embed this in a list. So for idoc in enumerate documents, so I'm going to append everything inside this results list here, and then what I'm going to do is I'm going to convert this list in string form. Now we only have one tool, which I will wrap inside this list. Then I'm going to bind my LLM using this tool with the help of the function bind tool, and then run this. Now we'll have our class agent state. It will be of type dict. I'll have messages, which will be an annotated sequence of base message, and then here what we want to do is we want to keep adding our messages. So I'm going to use this add messages function. And then I will define a router function, should continue state agent state. This will return the tool calls if it has. So what it is going to do is check if the last message contains tool calls. So for that, I'm going to see my last message, and then I'm going to return the result, tool calls, and len tool calls is greater than 0. Okay, so this is also done. Now what I'm going to do is I'm going to write a system prompt, which I'm going to copy from my source. So this is my system prompt. You are an intelligent AI assistant who answers questions about the stock market performance in 2024 based on the PDF document loaded into knowledge base. Use the retriever tool available to answer questions about the stock performance data. You can make multiple calls if needed. If you need to look up some information before asking a follow-up question, you're allowed to do that. Please always cite the specific parts of the document you use in our answers. So now what I'm going to do next is run this, and then I'm going to create a tool state. And then here I'm going to do our tool dot name, our tool for our tool in tool. So it should be tool, right? Yeah, in tool. Run this again. So this is also running. Now we'll define our LLM agent. So def call LLM. It will contain agent state. It will also return agent state. Agent state object. So function to call the LLM with the current state. So here what I'm going to do is I'm going to make a list of my messages. So list of state messages. Then I'm going to convert this into a system message, or I'm going to append my system prompt as well as the messages that we have. And finally, we're going to invoke our LLM using the combined message that we have. Okay, so this is done. I don't think I need to mention this messages. So I can just do message here. And then what I'm going to do is I'm going to return message, messages, list of message. Okay, this is also running. Now we create one more function for our retriever agent. So def take underscore action state agent state. It will also return agent state object. So what this function will do is this function to execute tools from the LLM's response. So for this, what I'm going to do is I'm going to check if we contain any tool calls from the LLM. So tool calls equals to system message -1 for tool calls. If there is, then we'll append everything inside results. So now we'll loop through our tool calls. So we'll try to understand what tool is being called here. So print f executing tool name with certain input. So if not the name in predict, I'll do tool not found. Or I can just keep it inside the result, but it's okay. I can keep it like this for now, but I don't want to directly append this. So what I'm going to do here is I'm going to do a result equals to tool not found, else I'm going to append this inside the results using the tool name. So t name dot invoke dargs dot get query and print tool result here. Then what I'm going to do is I'm going to append the tool message that we get from the above loop. So here results.append tool message. So tool call ID equals to t eid. What else? Name equals to tname and content equals to str result. This should be inside the for loop, sorry. And finally, I'm going to print tools executed, and then return the agent state response. Okay, now we build our graph using state graph, agent state. Add our first node, graph.add node, which will be our add node, which will be LLM represented by call LLM function. Then the second node will be add node. The second node will be retriever agent, which will be represented by take action function. Then the first edge will be graph.add edge. Add edge, it will go from start. I've not imported start, I guess. So let me also import start. So the first node will be from start to LLM. Then what I'll do is I'll add a conditional edge. Add conditional edge. This will go from LLM to should continue. And then we'll have two different cases here. For true, we'll go to retriever agent, and then if false, we'll go to end. I'll add one more edge here from retriever agent to LLM, and then the entry point will be from LLM itself. Okay, what's wrong with should continue? Let's see. Okay, the spelling is wrong here. Should underscore continue. Something's wrong here now. Function is not callable. Okay, let's rerun everything from the beginning. So this is running, tool collection is running, this is also running. The tool call is also running. Now the graph is also built. Let me compile the graph. Call it rag agent equal to graph.compile. And then if we print out our rag agent, then we should see our flow here. So from start, we go to LLM. If it has tool calls, then we go to retriever agent, then we go back to LLM. If it has multiple tool calls, we again reciprocate through these retriever agents. And then once our LLM call is complete, then we go to false and then end the conversation. So finally, we'll define a function for running our agents. So def running agent. So we'll use a continuous loop here, and then we'll ask the user for their question. Input what is your question? So if the user input is exit or quit, then we exit the agent. or else we're going to append the user given text into a human message. Then we will invoke our RAG agent. Then we'll print the agent response here. Okay, so this is also done. And finally, we'll call this running agent function. Since it was a long code, I hope we don't have any errors here, so we can run the application. Okay, so initially this is being run now. Okay, what do we ask here? So we'll ask what is the document about. Okay, we have an error. Let's see what the error is. I think I found my error here. So this should be inside a list. The system message should be inside a list here. Because if we don't keep it inside the list, then this is not considered as a base message. Let me read on everything again. Okay, so what is the document about? We still have an error. Let me check again. For this one, I'm also going to edit my retriever agent function. So let me rerun this again and then see if I get any error. So what is the document about? Let's see if we get any error. Okay, so the query is gone, and then we have two different sources from where we're getting result, and then the agent responses. The document is about stock market performance in 2024, specifically focusing on something. Okay, now we'll open this stock market document and then see what this document actually contains. What happened here? Okay, so let me rerun this again and then check. Meanwhile, I'm going to open this document. Okay, so this is our stock market document. It contains some data, and I will be asking question based on this here. So rerun everything again and then see if we can continuously talk to it or not, because I think we're getting some error there. We'll also fix that. Tell me about the EV leaders. Who is the electric vehicle leaders in the market? It should find that the EV leader vehicles are this company here. So the agent response is correctly given, and then we'll ask how much did they gain. So how much did Tesla gain in 2024? So from late 2023 to 2024 gains are occurring in there. So it contains a lot of content here. So it does give me the share price and then the growth as well as the sources as I asked earlier. So yeah, let me go to something else and then ask it. What was S and P's gain? So it should give me that S&P's gain was 25%. Okay, so this is working quite well. So this is how we implement RAG using our LangGraph. Okay, I'll ask it something that is not present in the document, and then we'll see what it tells us. So what is, why does the sun rises in the east and sets in the west? So it should not have any response for this. So it says, I cannot answer this question using the provided document as it was stock market performance and not astronomy. So this is working quite well. I'm going to end the video here. So I hope it implements on your end too. Be careful about the content of this particular function here, because there are too many brackets being involved here. So you might make some error. If you have any questions, feel free to comment down below and I'll try to help you out. And I'll see you in the next video again. Let me exit the system, and then it gracefully exits again.